Hello everyone. I wanted to make a quick video going over the Unit 2 practice exam so that you understand how all of these problems are solved and to answer any questions that might come up as you are working on it. Let's start with number 1. You have a glass bead with a given mass, it's 5 grams. It is subject to an electric field that is oriented toward the right. We can see that this bead is on a string that's connected to the ceiling and it's deviated 20 degrees from the vertical. So the electric field strength being given, that's 50,000 newtons per coulomb. We can ultimately figure out how much charge had to exist on the bead. So let's look at the free body diagram. On the left side, I have tension, I have the force coming from the electric field, and then I have the gravitational force. And the tension is broken into sine and cosine components so that I can demonstrate that the net force is equal to 0 in both directions. So that means T cosine theta is equal to Fg. That means T sine theta is equal to the product of the charge on the bead and the electric field strength. So let's start with the gravitational force. That is just mass times free fall acceleration. I retained a negative sign here just because of the coordinate system choice that I made, but it is the magnitude that you'll use to determine what T is. So the gravitational force is negative 0.049 newtons. That means that T cosine theta is exactly the same magnitude, but positive. Now the tension in the string can be found, 0.052 newtons. And now that I know the tension, I can use the angle that was given to figure out what T sine theta is. And when you do that, you get 0.0178 newtons. And finally, the charge on the bead, that is going to have to be equal to the ratio of T sine theta and the electric field strength, 50,000 newtons per coulomb. We have just one sig fig here from our 50,000 Newton per coulomb electric field strength. So you can write that as either 4 times 10 to the negative 7 coulombs, or I have it written as 0.4 microcoulombs. I don't care which units you use, and on the exam, unless it's specified, you can use either. Number 2, a proton and an electron are placed on the x-axis. How close would these particles need to be to exert 1 Newton of force on one another? This is like a simpler version of a problem that showed up in our lecture notes. Here you have just 2 charges, and we want the force to be a given value. I have the charge on each of these particles, and I know that they're going to be opposites, but I'm going to just use this version of Coulomb's law that takes the magnitude of Q1 and the magnitude of Q2, and I'm going to set that equal to just the magnitude of the force, 1.0 newtons. I know this force would be attractive, so if the proton were free to accelerate, it would accelerate toward the right. If the electron were free to accelerate, it would accelerate toward the left. Instead of Q1 and Q2, I just took the fundamental charges. So the magnitude is what's important here. So I just have lowercase e times lowercase e, and I can solve for the separation, which is lowercase r. What you get is 1.5 times 10 to the negative 14 meters. That is 2 sig figs coming from the force, which is given to 2 sig figs. Now, number 3, this is just like the one that we solved in the electric charges and fields and forces chapter. We have 2 known charges. We know they are both positive this time, and we want to figure out where a third charge can be placed such that it experiences 0 net force. We need the net force on that unknown charge 3 to be equal to 0. So the force of 1 on 3 has to be enough to balance the magnitude of the force of 2 on 3. So I went from vectors to magnitudes on this step here. I canceled out like terms. So the Q3, that value does not need to be known in order to answer this question. And I canceled out the electrostatic constant K. And the next thing I needed to do was to find some way to communicate where charge 3 was relative to each of the charges positions I know. And I think we did this differently in the notes, but this time I chose the distance between charge 3 and the 8 microcoulomb charge to be 50 minus d. The distance between the 3 microcoulomb charge and Q3 was d. So I could use the FOIL method to figure out what 50 centimeters minus d quantity squared gives you. You end up with a quadratic. There will be a negative term or a negative root that's not relevant here. And I just stuck with centimeters and microcoulombs. So the distance that I calculated was also in centimeters. You end up with 19 centimeters to 2 sig figs. The next group of questions, I'll deal with the system of point charges shown below. We have 2 positives, 1 negative, and the magnitudes are 1, 2, and 3 microcoulombs. They make an equilateral triangle, so I know all of the interior angles are 60 degrees, and the length of each side is 20 centimeters. First, we need the magnitude and direction of the force on the 3.0 microcoulomb charge. So I can just use Coulomb's law, and once again, I'm just sticking with microcoulombs and centimeters. K is not going to cancel out this time, so I'm using the version that is in microcoulombs and centimeters. So usually I used 89.9 just to preserve 3 sig figs. In this case, I rounded to 90. So the force from charge 1 on charge number 3 is K times Q1, Q2 over R squared. I get 0.675 newtons, and because this is an equilateral triangle, I know that R is going to be exactly the same value for F2 on 3. All I need to do is switch out Q2 in favor of Q1. So instead of 1 microcoulomb, switch to the 2 microcoulomb charge. And what is kind of left unsaid here, but will be relevant in a moment, is that since charge 1 and 3 are both positive, this 0.675 or 675 newtons is going to be repulsive. I have unlike charges when I look at 2 and 3. So this 1.35 Newton force is going to be an attractive one. So I have the 2 force values coming from 1 on 3 and then 2 on 3. I can split that up using the 60-degree interior angle that's acting on the 3 microcoulomb charge. So the dotted lines that make up the sides of the equilateral triangles are also going to give me information about the orientation of these force vectors. So I have a 60-degree angle with the horizontal each time. I'll take cosine 60 for the x components. I'll take sine 60 for the y components. And one of my y components, F2 on 3, is going to be a negative, so I have to treat that as a negative. And I end up with F net x and F net y. I can combine those to find the magnitude of that vector. I get something that rounds to 1.2 newtons. And here's a place where it's easy to make a mistake. The net force component in the x and the y direction are going to make an angle that is not 60 degrees. It's not the same as what we saw previously. So to figure out what that angle truly is, just take the arcsine of this angle, alpha in this case. So that's F net y over F net x. That's how you get negative 30 degrees. Now for number 5, if I calculate the total electrical potential energy of that system of charges, I need to take into account all 3 of the pairs that I can build. So the total potential energy is going to involve the potential energy of just 1 and 2, just 2 and 3, and then finally 1 and 3. Since R is going to be the same for each one, each charge is 20 centimeters away from the other 2. I can pull R out front, and I just have these products, Q1, Q2, Q3, Q2, and then Q1, Q3. Looks like I forgot to write actually 2 Q's there, so this should be Q1 times Q3. That's how we end up with charges that are given in square coulombs, and they're to the negative 12th power. So because I'm looking for an energy in joules, I am using the version of K that has newtons, meters, and then coulombs in it. You end up with a negative potential energy. So that is negative 0.22 joules to the appropriate number of sig figs. Number 6 deals with the electric field at point P. So if we go further up, you'll see that point P is right here at the base of this equilateral triangle. So point P is 10 centimeters away from the 1 microcoulomb charge. It's 10 centimeters away from the 2.0 microcoulomb charge, but it's a different distance away from the 3.0 microcoulomb. And that distance is not just 20 centimeters. I can use the Pythagorean theorem, or I can use an interior angle, some way to figure out what the vertical leg of this right triangle is. So if I take the sine of 60 degrees with the hypotenuse 20 centimeters, I can find that h can be expressed as the square root of 300 centimeters. You could also do this with 0.2 meters and 0.1 meters. So because I chose centimeters, I'm going to end up with an electric field that's given in newtons per microcoulomb. So again, I use the version of K that involves centimeters and microcoulombs. And now this expression is just calculating the field due to charge 1, charge 2, and charge 3 at position P. I don't need to know anything about the imaginary probe charge I'm placing at position P. So for R1, that's the 10 centimeter separation from point P. Charge 2 is also 10 centimeters away from point P. Charge 3 is radical 300 centimeters away. So I get 0.90, negative 1.8, and then 0.90 newtons per coulomb. Now, it can be tempting to take these three electric field values and treat them as if they are x, y, and z components where you're computing the magnitude of a vector. But if you take a look at what the free body diagram, or I guess more realistically, just what your field diagram would look like at point P, the field produced by charge 1 is going to be oriented toward the right because that charge is a positive. So we can imagine field vectors just coming out of that positive charge. The 2.0 microcoulomb charge is a negative, so we imagine field vectors pointing toward that charge. And then finally, for the positive 3 microcoulomb point charge, we can imagine electric field vectors at point P pointing straight down. So that translates to 2 vectors that point toward the right. They have different magnitudes, and I have just one vector that is oriented along the negative y-axis. So E net is going to point into quadrant number 4. Combine E1 and E2 first to get the net field in the x direction. Then square that, add it to the square of E squared, which is itself just the net field in the y direction, quantity squared. And I get 2.8 newtons per microcoulomb. If you did this process using coulombs and meters instead, you would get 2.8 to the negative 6 newtons per coulomb. And then finally, I'm calculating the angle between the net field vector and the positive x axis by taking an inverse tangent and using the x and the y components as I know them. Finally, the electric potential at point P, or in other words, the scalar potential, that's a term I used there as well, that's going to be equal to K times Q1 over R1, where I am going to work with the version of K that has meters and coulombs in there because I need to get to a volt. And a volt is a joule per coulomb. So I don't want centimeters, I don't want microcoulombs. So we can figure out or actually just reuse the distances between each one of our charges in point P. So that goes from 10 centimeters to 0.10 meters, and then your vertical leg, the distance between charge 3 and point P, is now the square root of 0.030 meters, not just the square root of 300 with 2 decimal places moved over. And you end up with 3 different potentials. They all overlap at position P, so you can add them together. That is 6.6 times 10 to the positive 4 volts. So for 8, the amount of work that would need to be done to move the 3 microcoulomb point charge to point P. So for them to be in a line instead of an equilateral triangle, all I would need to do is determine the potential energy of the original orientation of the original system of point charges, which we already know, and I can compare that to the electric potential energy of the new arrangement of charges, where the 3.0 microcoulomb charge is right in between the positive 1 and the negative 2. I need to evaluate all of the available pairs again, so I have a 20 centimeter separation between the 1 and the 2 microcoulomb charge, and then just a 10 centimeter separation between the remaining pairs. That's where 0.20 and 0.10 and 0.10 come from. So sum that up, you get negative 0.3596 joules. And comparing that to the original potential energy, if I take the final energy minus the initial, I end up with negative 0.13485 joules, which is itself the negative of the amount of work done. So in other words, calculate delta U, multiply that by negative 1, and you have work. That is 0.13 joules. Next, we have a parallel plate capacitor with plates of a given area, and we have a separation that is also known. It's connected to 2 6-volt batteries in series, so that essentially means that the potential difference from the bottom terminal of the lower battery to the upper terminal of the upper battery is going to be 12 volts, so 2 times 6 volts. And if the positive terminals are oriented upward, that tells me that the electric field inside this capacitor is going to be pointing down just by tracing the path that positive charges would take. I have a potential difference, delta V total, which is 12 volts total. I know that's going to be equal to the amount of work, chemical work that's being done on those charges per unit charge. The charge carriers are going to have magnitude E. So each one of those is going to require 1.9 times 10 to the negative 18 joules of work to go from the bottom of the chain to the top of the chain of batteries. The capacitance value is something that is independent of delta V. That's something I could calculate just by knowing the area, the separation between plates, and the permittivity. So doing that gives us 3.0 times 10 to the negative 12 farad. And this is a picofarad, 3.0 picofarad. I'm not certain that we've run into pico anything yet before this, but that is the appropriate prefix you could use for it. I have now enough information to figure out the magnitude of the charge on each plate. Because I know that delta V for the capacitor is eventually going to be the same as delta V for my chain of batteries. So that's going to be 12 volts. I know the capacitance value, and I left the units in coulombs squared over newtons times meters here because I could take the volt, write it as a joule per coulomb, and it becomes really clear where the rest of the unit cancellation happens. This is 3.5 times 10 to the negative 11 coulombs. Now the magnitude of the electric field in the region between the plates, that's just going to be equal to the ratio of delta V between the plates of the capacitor and the separation, which was given. So this number 12 is also something I could have calculated before I knew anything about Q, or even before I knew anything about the capacitance value. This is 4,000 volts per meter, so 4.0 times 10 to the positive 3 volts per meter to the appropriate number of sig figs. Moving on, that electric field is capable of storing potential energy, and since I know the potential difference between the plates and I know the capacitance at this point, I can figure out how much energy is in that field. So U sub C, that's the potential energy in the capacitor field, is just 1/2 the capacitance times the square of delta V. That is where 2.1 times 10 to the negative 10 joules comes from. And just as I did before, I split the volt into joules and coulombs, and I split the farad into coulomb squared per joule. That shows that both of your coulomb squared cancel, and one of the joules that's in the numerator is left behind when the one that's in the denominator cancels. 14, the energy density of the region between the plates. I chose to calculate this using the energy density equation, where E refers to the electric field, but there's also another way that I could have done that would give you exactly the same value. I looked up the permittivity constant in coulomb squared, newtons, and meters squared. That will be on your formula sheet. I already know the electric field strength, so I can just plug and chug. The units here get a little bit complicated, but I took volts squared and split it initially into a joule and a coulomb squared. There's a meter that's in the denominator of that statement that's also going to be squared. And I split the joule into a newton and a meter. So that's newton squared, meter squared. We can cancel out everything except for 1 newton and 1 meter that exist in the numerator, and then 3 meters that stick around in the denominator. So we're going to have joules per meter cubed. 15, if a few sheets of paper are slid into the region between plates, what would be the new electric field strength? The kappa value for paper is in a table in our textbook. That's not something I'd expect you to know on your own, so I would give it to you unless you were calculating it. So that's 3.7. So the electric field inside of the capacitor now is going to be weaker because of the presence of that dielectric. 4,000 volts per meter divided by 3.7. That is a unitless quantity. Now we have 1,100 volts per meter. And 16, if the paper is removed, but the plate separation is increased to 5 millimeters, what voltage would be required to match the original electric field strength? I can go back to the electric field strength that we calculated a few steps earlier and our new plate separation to find that the product of those two would give me the new delta V. So this would require 20 volts. So I could take a 20 volt power supply, perhaps, or I could just arrange batteries such that the chain in series gives you 20 volts. Number 17, we have a graph of electric field in the X direction versus position. And the position is given in centimeters. The electric field is given in volts per meter. So there's some unit conversion that is going to happen before I compute the area below this curve. But I can split it up into 1 centimeter chunks just so that we have a little bit more guidance when it comes to sketching what this graph would look like. So each one of these yellow triangles has the same height, 1.5 volts. It has the same width or the same base, 0.01 meters instead of just 1 centimeter. So half of that is going to give you 0.0075 volts. I have 1, 2, 3, 4 of these. The remaining sections I can express as rectangles. So now I have a rectangle that has a height of 6.5 volts per meter, a width of 1 centimeter. So when you do your unit conversion, this gives you 0.065. My next rectangle is 5 volts per meter tall. The next one is 3.5 volts per meter tall. And then these last two blue ones are both 2 volts per meter tall. So when you sum those together, the total potential difference measured from x is equal to 0, which is the given point where the potential is 0, all the way up to x is equal to 5 centimeters, this will give you negative 0.227 volts. Negative because delta V is the negative of the area below this curve, and the area below the curve that we calculate is a positive value. So next, since we did that in 1 centimeter increments, we can make a graph of potential versus position where all of the ordered pairs are shown here in the left, and it's just a matter of plotting them. So all of these potentials are negative values. for exactly the same reason that we needed to use a negative sign right here and also right here. So I have one slope value between segment 1, I have a slope value between segment 2, and each one of these points is connected with its own delta V, more or less. So if I take one of these yellow triangles and stack it on top of the rectangle that traces out, or that encompasses this 1 centimeter jump, each time I'm going to end up with a different value. Last but not least, what if we do the opposite? We've got a graph of potential versus the horizontal position. The position's given in centimeters again. And I can see the potential begins at 8 volts. It consistently drops off to 2 volts by the time you get to x is equal to 4 centimeters. And then it is constant from x is equal to 4 to x is equal to 5. So since last time we needed to compute the integral of our electric field function and then multiply that through by -1, this time calculating the derivative and multiplying by -1 will give us what we need so that we can calculate, or we can determine, the electric field strength at x is equal to 5. So the first 4 centimeters I can use, or I can group together, and I can use to figure out what the slope of that line is. That's going to be negative 150 volts per meter. Again, where the run portion of this has already been converted into meters. So 2 minus 8 divided by 0.040 gives you negative 150, and then you have a horizontal section, so that's a 0 slope. That means that the electric field is constant over the first 4 centimeters, and then a different constant value over the last centimeter. I can take 150 volts per meter and then multiply through by -1 to turn that into 150 volts per meter. That's a constant value because the slope of the upper graph does not change until I get to 4 centimeters. Drop down. Now the slope of the last piece of this graph was 0, so the electric field strength at that position is equal to 0. In other words, the negative of the derivative of position potential with respect to position is equal to the electric field. Hello, everyone. I wanted to go over some pointers so that you know what you should expect to see in our exam that's coming up on Monday. You have 4 chapters to review. Chapter 22, which is electric charges and forces. 23, which is the electric field. We skipped 24, but we went to 25, which is the electric potential. And then 26 is potential and field. I'm going to ask you a question about systems of point charges. So there are 4 possible things you could do with a system of point charges. I'm going to ask you to do 2 of them. So it might be finding the force on one charge from all the others. It might be finding the field produced by a group of charges. It might be calculating the electric potential energy of a group of charges. And it might be calculating the electric potential due to a group of charges. So there are good example problems from our lecture notes to review for the force on one charge from the others. Look for the second half of the chapter 22 lecture notes. We did an example like that. The field produced by a group of charges, I believe it's the first half of chapter 23's class notes that has an example. The electric potential energy and the electric potential due to a group of charges are both found in chapter 25. Next, the electric field inside of a capacitor. We did a problem like this in, I believe it's the second half of chapter 23's class notes. So that's a good one to review. I'm going to ask you about finding the electric field from a graph of potential versus position, or finding the potential from a graph of electric field versus position. So make sure that you review so you know which one of those two is the negative of the graph's derivative and which one is the negative of the graph's integral. And number 4, I'm going to ask you about groups of capacitors, but it will not be as complex as the example we went over in class. Your questions will be either all series or all parallel, but nothing in between. I have something going on at 1 o'clock tomorrow morning, or tomorrow afternoon, so that's going to be October 27th on Friday. So my office hours are going to go from 10:30 to about 12:45 instead of to the entire 1:30. But you still have the option to send messages on Canvas if you have questions about anything, and that extends over the weekend as well.